Okay, so in the main video I described how we make coproducts in set to the power of C, and now I want to prove that they have the kind of properties that they should have. So the first thing to do is to show that when we kind of define the coproduct like this, so these are the E-type elements and this is how the S action works, in that kind of case, we do have a proper functor A plus B from C to set. Okay, so that's the first thing we want to establish. So remember, the S action is defined like this. So for gamma comma K in A plus B of E, the S action either sends that to A of S of gamma if K equals 0, or B of S of either sends it to A of S of gamma comma 0 if K equals 0, or B of S of gamma of 1 if K equals 1. So clearly then A plus B of S is indeed a function from A plus B of E to A plus B of V. So it is indeed, I mean, we could basically think of this as the kind of lifting of this arrow S of C under this functor A plus B, and it is indeed a proper, well, it has the right kind of source and target after it's been lifted, because it goes from A plus B of E to A plus B of V. Now, we want to show that this kind of thing satisfies the functor laws. So suppose we have gamma comma K in A plus B of E. Well, we'll just do the case where K equals 0, because the case with K equals 1 is basically looks just the same, so no point sort of going over sort of duplicate logic. So we want to show that this kind of thing satisfies the proper law of the functor, in particular that A plus B of R after S equals A plus B of R after A plus B of S, where we have an arrow S from E to V and an arrow R from V to W in this category C. So how can we see this? Well, if we do A plus B of R of S on our general kind of element, gamma comma K, where we'll assume that K is 0, well then the result will be A of RS of gamma comma 0. And because A is a functor, we can write this as A of R after A of S operating on gamma comma 0. But if you look at this is actually equal to this, which is A plus B of R operating on A of S of gamma comma 0. Because if you think about how this operates, when you operate it, you see, oh, I've got a 0 there, so I'll just do A of R on here and get this. Okay, and similarly, this thing inside the brackets, again, we can replace this with A plus B of S operating on gamma comma K. And so we have for this general element that doing A plus B of R of S on it gives us the same thing as doing A plus B of S on it and then A plus B of R on it. Well, okay, in this argument, I suppose K equals 0, but we could repeat the argument when K equals 1 as well. So it works. This kind of law, basically, that this thing is equal to this thing, this kind of functor law holds. So the only other thing we need to check is that this thing satisfies the functor law involving the identities. So again, we'll assume K equals 0 just because we don't want to duplicate thinking. It's faster this way. You can fill in the K equals 1 case for yourself. So A plus B of identity E of gamma comma 0, that's going to give us A of identity E of gamma, comma 0, which is just the identity arrow of A of E working on gamma, comma 0, which is just gamma, comma 0, which is just the identity of A plus B of E operating on gamma, comma 0. So yeah, this works out. And similarly, it would work out when k equals 1. So that proves that indeed we do have that A plus B, as I've defined it, forms a functor from C to set. Now, there are other kinds of arrows involved in the kind of setup which I've described, and we want to now show that they are indeed natural transformations. So one of these arrows is I1. Okay, so we really want to show that I1 is a natural transformation from A to A plus B. So we'll look at the E-type elements. We'll imagine we have this arrow S from E to V, and then we want to show that this is a naturality square. So if we take a theta in A of E, if we do the eth component of I of 1 on that, we get theta comma 0. And then if we do A plus B of S on that, then we get A plus B of S operating on theta comma 0. So that's what happens when we go along the top and the right of this square. What about the other way around? Well, if we start with theta, we do A of S on it, we get A of S of theta. Then if we do the V component of I of 1 on it, well, that's just going to append a 0, so we get A of S of theta comma 0. But now if we know how A plus B of S works, we actually know that this is equal to this. So yes, this is a natural square, and that means that I1 is a natural transformation from A to A plus B. And by similar reasoning, you can show that I2 is a natural transformation from B to A plus B. So the other thing we want to show then is that this F comma G arrow, which is an arrow from A plus B to X, is a natural transformation. Remember, we're supposing that F is an arrow from A to X and G is an arrow from B to X. So how can we see that this is a natural transformation? Well, again, we just sort of want to prove that this is a naturality square. So we start with a gamma comma 0 up here. Again, we're going to sort of suppose that k is 0 because we'll just do this reasoning, and then the reasoning with k equals 1 is similar. So, you know, we don't need to bother going through that. So we'll start with gamma comma 0, and then when we do f comma g of e of that, the eth component of f comma g on that, the result is going to be f of e of gamma. And then when we do this s action in x, and then when we do this s action in x, we get the result x of s of f of e of gamma. Now, going the other way around the naturality square, when we do a plus b of s on gamma comma 0, we get a of s of gamma comma 0. And then when we do the v component of f comma g, we get f of v of a of s of gamma. Now, why are these two things equal? Well, they're equal basically because f is a natural transformation from a to x. So if we just think about gamma belonging to a of e and draw up a naturality square, we'll get this equation. So we know that this holds, and so we know that f comma g is a natural transformation. Okay, so we've shown now that all our kind of objects and arrows which we've defined are properly defined kind of things in set to the power of c. Finally, then, we just need to show that like the universal property is satisfied, that we really do have a categorical product. So firstly, we want to show that this f comma g, which we've defined, does indeed make this kind of diagram commute. So suppose we have a theta in a of e, well then if we do f comma g, well then if we do the ETH component of f comma g after the ETH component of I on theta, that's going to be what we get if we do the ETH component of f comma g on theta comma 0, which is going to be f of e of theta. And so that means this upper triangle commutes. And by similar reasoning, starting with the theta in b of e, you can show that this lower triangle commutes as well. So yes, f comma g does make this diagram commute. Now, the other thing we want to show is that this is the only arrow that does this. So we want to show that this is a unique arrow that makes this kind of thing commute. So let's suppose we have some gamma, which is some arrow from a plus b to x, and we'll suppose that gamma is not equal to f comma g. And then basically we want to show that gamma can't make this kind of diagram commute. So since we're assuming gamma is not equal to f comma g, that means that there exists some capital E in C and some phi comma k in a plus b, which is such that doing the ETH component of gamma on phi comma k does not equal what we get if we do the ETH component of f comma g on phi comma k. Now we're going to suppose that k equals 0, and we'll go for an argument, and we'll basically show that that means that this gamma can't make this diagram commute. And you can repeat this argument supposing k equals 1, but you know it's similar, so I'll just go through the k equals 0 case. So for phi in a of e, we're going to have that doing the ETH component of I1 on phi gives us phi comma 0, which we'll write as phi comma k. And now what we're going to have is that doing the ETH component of gamma after doing the ETH component of I1 on phi, well, we know that's not equal to what we get if we do the ETH component of f comma g. After I1 subscript e on phi, because, you know, we have it doing that ETH component of I1 of e on phi gives us this, and we have this kind of inequality here. So we have this inequality here, but this thing on the right is just equal to what we get if we do the ETH component of f on phi here. And so then that implies that it's not true that doing gamma after I1 equals f in this case. So this is the case we get when we suppose that the kind of gamma comma k for which this kind of thing fails has k equals 0. If we had k equals 1 instead, then we'd get that gamma I2 does not equal g. So either way, basically if we use any arrow gamma that's different from f comma g, then it's not going to make this diagram commute. So that means that this f comma g is indeed the only arrow which makes this diagram commute. And that completes the proof that we have the coproduct a plus b of a and b.